Okay, so let's start it. So hi everyone, I'm the Kai Jin, a staff scientist and tech lead at Alibaba Damo Academy. So today it's our pleasure to invite Dr. Theodore Zhao to present his work. It's unifying the biomedical segmentation task with language. So Theodore is a senior applied scientist at Microsoft Health and Life Science Research, working on multimodal biomedical imaging models as well as biomedical natural language processing. So Theodore earned his PhD in applied mathematics degree from University of Washington, so where his research applied machine learning, stochastic modeling, and optimization to applications in finance and healthcare. So his research interests focus on machine learning, self-supervised learning, multimodal modelings, and stochastic modelings. So let's turn the time to Theodore. Let's welcome for his presentation. Go ahead,
Thank
Theodore.
you. Thank you, Doctor, for the introduction. It's my pleasure to present this topic, unifying biomedical segmentation tasks with language. Let's get right started. So this slide is about some overview about biomed image analysis. So usually there for biomedical image, there are a lot of questions that we care about. For example, in this MRI, we care about what's the size of the tumor in the brain and what part of the tumor is necrotic. And in this X-ray scan, we care about if the patient is infected and how much of the lung is infected. And in another very different pathological slides, we also care about is there any neoplastic cells in this image, and if there are any immune cells near the neoplastic cells. So all these different questions we want to ask, they can somehow be related to the broad topic of semantic segmentation, which is associated region in the image with some certain medical concepts. So there are many different modalities for biomedical images, for example, X-rays, CT, MRIs, pathology, etc. And there are so many different segmentation targets, sometimes we want to segment organs, sometimes lesions, sometimes cells. It's a very broad category of modality image type and also the segmentation target type. So traditionally, we usually train multiple specialist models. For example, one model for segmenting this tumor region in MRI, another model for segmenting some cellular structures in pathology, sometimes in infected region in CTs. There have always been the attempt to try to unify different tests into a single foundation model. And thanks to the introduction of the segment anything model, previously we were able to unify all different biomedical segmentation tests with one model, which is the previous work called MICCAI. And I believe many of you are very familiar with this one. And with MICCAI, the user can provide some manual input for every object, and the model can unify all different segmentation masks in this interactive prompting manner that we can achieve some goals traditionally by many different specific models, but now one with a single foundation model. However, we wanted to ask the question if this is the exact right way to unify all these different tasks. And one thing that we thought about is the story in NLP. So it's not many years ago, I believe this maybe just only 5 years ago, NLP was still occupied by so many different tasks. Sometimes name entity recognition, sometimes question answering, summarization, translation, and so on. I can name maybe 20 or even more different subtasks in NLP that different models were designed to tackle different problems. And by the time the GPT-2 model, the title was Language Models are Multitask Learners. And there is a way that all these different tasks can be now unified in the same framework. And this framework, if you think about it, is to define the tasks by designing different prompts. And this prompt is natural language. And the key in the natural language is that is very, very expressive because it contains many things that the human knowledge contains and human can express. So it's very versatile. And another key advantage of the natural language is that it is the key for modern LLM because it's very scalable to solve different tasks. And it's also related to some like agent framework because language is a very universal interface that can interact with outside of the model. So if you take the same thought into the same problem, the hope our hope was that we want to unify all the tasks by language and only the language. And by doing so, we want to tell the model what to do with certain medical concepts. For example, if you want to segment different things in different image, you simply just spell out the tasks or like what you want to segment in natural language. And this natural language can have some like variety. If you if you prompt the model in different way, the model should know what's different parts of the image it should go to. So this is the broad problem outline. And in this talk, I want to introduce like three parts. The first part is it possible to unify by language and how? So basically, it's like you can think of like it's like a proof of concepts or like to know if this is ever possible. And I will present our work BiomedParse, which was like the first one that's doing this task. And I will also introduce some of the remaining challenges with coming with localization with language only. And I will at the third part, I will talk about how we can scale like a 2D model to solve 3D problems. So let's to the first part. So the first part is unifying tasks and modalities with language. And the first thing that we did in order to solve this task is to define a segmentation task. Just the same as like you design a prompt to unify all the different NLP problems. You also need to have a unified like a structured way to design segmentation task. And if you think about it, there are three components that are can almost uniquely define a segmentation task. First one is how was the image created? So this is you can basically the modality of the image. What's the technology that you use to create this image? And this makes the image very differently. So the model should know that in order to perform high quality segmentation. The second is where was the imaging was performed? Is it like in the chest or is it in the abdomen or is like in the low limb or is the brain? And that way the model can tell like which part I should be looking for and what are the possible anatomies in this image. And the last one is the most important one is what is the target to segment? Are you segmenting like infected regions or segmenting certain type of like organs? And this is actually the key because in the same image, what we want to achieve that is that you prompt the model in different ways. The model should know go to different parts of the image. And with this like three components, we can almost uniquely define a segmentation task. And we found that this actually is available in most of the data sets that we can access. For example, in one type of segmentation task data sets, usually the modality is fixed. Sometimes we just do, let's say, X-ray segmentation in X-ray. And usually also the site of the imaging was also spelled out, so we can get this type of information. And lastly, each segmentation datasets have the associated class types and which is the object types that we can use to create this like a task definition. So by using this definition, we created the first text segmentation data sets. And it contains like more than like 6 million image and text pairs and derived from 45 public data sets. And the creation of the data sets was using at that time like a GPT-4 model to create these prompts. So basically unifying the three components and tell GPT-4 to generate a variety of description of the same task, but keeping like all the three components the same as they are. And we have open sourced these data sets on Hugging Face. And you can train like your model using this like text prompt to do the segmentation. So each of the example will include a prompt, a image, and the corresponding segmentation, ground truth segmentation mask. So this data set covers like a big variety of modalities. It covers like in total 9 different modalities from CT, MRI, X-ray to dermoscopy and OCT, and also many different anatomy sites in each of the modality. And also covers like a different type of the objects, and each of them is actually defined by prompts. So it's not the fixed sets of classes, but each of them, if you describe with different text prompts, it's referring to different classes. So that's very extendable to new object types. So once you have the models, the next important thing is the model architecture. So we used the SEAM, the segment everything everywhere model architecture, because of its incorporation of the language modules and the image encoder, so that you can perform like a text prompted segmentation. And this architecture is very similar to many modern like promptable segmentation architecture like SAM, but we just use the text encoders to indicate the where the user want to perform the segmentation. We have also open sourced this model, Hugging Face. So some of the examples. So the input is just the text prompts describing the modality and object types, and output is the corresponding segmentation tasks. And we proved that in this framework, if we train on enough data, and the model will be able to deliver like segmentation tasks in the corresponding way. Here are some like a quick overall comparison with other models. So we compared at that time because there was less like text promptable segmentation model. So we compared with the bounding box segmentation model, which is the model precisely where is the object using a Oracle bounding box. And surprisingly, we were able to outperform the promptable segment, the bounding box prompts models, and also like a text to box models. And we also conducted some comparison with expert models. Like we train on every specific data sets. We train a specific InnerUnet and DeepLab V3, and the performance of BiomedParse on each individual tasks was comparable with the supervised expert models. And so here I want to introduce some like analysis of like the advantage of using text, because it sounds very a bit counterintuitive. Like if you provide the location of the object to the model using a bounding box prompt, why is it possible that when you don't provide it, you are achieving even better performance? Is that even possible? But if you think of like from the information, the amount of information perspective, it's actually very understandable. So how many dimensions do you need to represent one bounding box? The answer is 4. You need just the coordinates of the corners of the bounding box which is XY, Y1, X1, Y1, and X2, Y2, and that can uniquely define a bounding box. So that means the amount of information in terms of dimension for a bounding box is 4. So what's the dimension of a text prompt? So if we think about like some typical language model, you will find out that the dimension of the text embedding is somewhere around like a few hundreds. So this is much larger than the dimension of the a bounding box. And so in that comparison, we know that the text is much more expressive than these like spatial prompts. It's very efficient. And this example shows that in some like certain circumstances, using a bounding box sometimes can be very ambiguous and not pointing to the exact ideal like target in mind. And this is also because of the less expressiveness of this like low dimensional input. And because of that, we also conduct some like analysis showing what's the improvements over like the bounding box-based methods. And we found that if the object becomes like more irregular, there is more advantage because in that region of the prompts, for example, like when the box ratio is very low, which is the area of the ground truth mass inside the box, the advantage, it's very hard for a spatial prompt model to accurately go to the object type that's asked about. Here's some just quick notes on the fine tuning. We also try like using like 10 scans to fine tune the model, and with just 10 scans starting from the pre-trained model, it's able to pick up to a pretty good state, not to the perfect level, but to a good level compared to other models. So I want to just a quick summary here. So with this work of BiomedParse, what we know. So we know that it is possible to unify different biomedical modality and segmentation tasks only with language and without any other spatial prompting. And it's able to match the performance of text-specific models and surpass even like interactive prompting models. And the data sets was created with prompts from the LLM, and that can facilitate like other work. And there is also the pre-trained model with the theme architecture. So with that, there are still some remaining challenges that I will cover in the next part of the talk. The first one is locating object purely by text prompt is not easy, especially when the object is very small. And the second one is 2D models naturally lack the 3D context when working on modalities like CT and MRI. Oh, I think I can pause here. I saw there are hands up. Maybe I can pause here to take some questions.
So Theodore, I think right now we haven't seen the questions typed in the QA section, and so if you have any questions, you can type your questions in the QA section. And we can address. Theodore can address the
Yeah,
question by then.
good.
I think right now, since no questions yet, you may continue. And there's one question. So Theodore, you want right now to stop and answer question, or you want to finish all and then we read all the questions one by one?
I can address this question. The question is, could you elaborate the generation text, because I would be interested in how you assess the label quality. Okay, yeah, I can quickly address this one. So the creation of the text is to prompt the model, prompt the LLM with the this like a triplet definition, object type, what's the object type, what's the modality of the image, and what's the site of the image. and the LLM will be asked to generate like for every single task, generate a variety of different prompts. So the checking the quality is not a tedious task because there are just a limited number of publicly available data sets and also tasks. So you can just manually check if each of the prompts containing the required information, and if it contains like other information or false information, you can simply just delete that prompt. So this prompt is not image specific, but dataset specific. So that's make the work less tedious. The second question is the correlation between the text prompt and the segmented area similar to the method developed for, oh, sorry, DALI models? Sorry, I'm not so familiar with this one. Yeah, so I cannot provide a good answer. Yeah, I can address the next question first. If text is understood primarily the configuration triples, then doesn't it intrinsically receive the information by text? Yeah, it's a good point. So the triple definition, but actually you can have different modalities and sites and detection types. So the combinatory total number of available tasks can be much, much larger. But it's a very, very good point, is that even though the text embedding is about like hundreds of dimensions, the total effective number of knowledge from the text actually depends on your training data. So if your data, so let's imagine you train this model just with one text. So let's say this like COVID-19 in CXR task. Then your model will only be able to know this type of text. So effectively, the text embedding, even though the dimension, let's say, is like a 512, the effective dimension or the dimension of the manifold, effective manifold, is actually much, 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 much smaller than that dimension. But if you train with more variety of different tasks, the effective dimension of the text will grow. Well, the upper bound is the upper bound set by the language model, let's say a few hundred, but the effective one will grow with your training data sets. So yeah, I will also like, address this. Actually, it's one of the limitations that if you don't train with a variety of tasks, it cannot expand to like unseen tasks because of that. But yeah, it's a very good point.
Yeah. So Theodore, how about I read the question. You can focus on answering them.
Okay.
So following the previous one, so one audience asked how to understand the dimension of the bounding box is only 4, but the text is 512, because bounding box in SAM model is embedding by the prompt encoder, and it will become a query token with the shape of 4 by 512 or similar to that. Like you talk about that in the feature level. That's
Not the feature, but the number of effective number of dimension for the information. So let's say you can always scale up the representation of specific information into a higher dimensional embedding. The purpose is that you want to match the dimension of other components. But when you do that dimension scaling up, the effective rank of the so-called position embedding actually is not that much. So the information from the source of those like prompts, encoded prompts, are actually can be only defined with like four numbers. Let's talk about like a 2D images. It's like the x1, y1, x2, y2. Only four. You can uniquely define a boundary box inside any image. And when using the positional embedding, we scale up. We use like the different frequencies to represent, but it's still like just one location. The amount of information here is 4, but you can scale up to higher dimension in order to be compatible with the embeddings from other parts of the model. Yeah, I hope that answers the question.
Yeah, thank you, Theodore. So the other audience is asking, unlike prompts such as box and point, which contain the spatial information, how does text prompt solve the problem of lack of spatial information?
Mhm. Yeah, it's very hard. I would say it's challenging because lack of the spatial information you are going. So let's say when you given this prompt, you know that the object is just something inside here. But lack of that, you are like trying to find this from the whole image. So it is naturally hard, and I will introduce in the next part the specific challenging case when the object is very small and how we tackle that.
Okay. And the other audience is asking, was clip used for training to match the specific label mask to specific text label? For example,
Uh,
in the tumor.
no,
I don't.
no, we didn't. We didn't train a specific clip for this purpose.
Right. And another audience is asking, do we need to provide the model with triplets of prompts like modality, organ, tumor, or how well the model perform if we lack some of the information?
Uh, so the key information is the object type. Because ideally you can imagine if you input this image to the model should be able to classify what's the modality is of the image and what's the uh, site of the image. So the other two information actually they can be ignored, but the object type is necessary. Otherwise, the model doesn't know where to go to. So that's the key information. So we experimented with like a different type of prompt. Sometimes only naming the targets to segment, and it also works. So it's pretty robust to that variation.
Mm. Okay, yeah, thank you, Theodore. I think right now that's all the questions, and you may continue. And for the audience, if you have questions, you can continue type in the Q&A section. So Theodore will answer the question after he finished the rest part of his presentation. Okay,
Yeah,
thank you, Theodore.
thank you. Uh, yeah, in the second part, I will introduce how to precisely locate small object with language. And so on the right side is a error case of BiomedParse. So the task was to segmenting like a long nodule in CT scans. So the red one is the ground truth, is very, very tiny, and the green is the prediction from the model. So clearly the model prediction is like completely missing the ground truth. So what's the reason for this failure? Uh, so if you think about from like the transformer or the attention mechanism, it is a problem of like a needle in a haystack. So the in medical image segmentation, a lot of times the object of interest can be smaller than even 0.1% of the image. And in this specific case, I believe it's even smaller. And if you look at the how attention score is calculated in every like transformer-based models, you will find out that there the related parts of the feature is very, very small parts. And when there are so many other like image patches, the denominator can grow very large. So the total number of like attention score that can be effectively used for these like small regions is smaller. So this can be hard to focus on without the spatial prompts. Because if you have a spatial prompts, you can always like try to narrow down the region, and it's easier for the model to know what to do. But without any spatial prompting, only using language trying to locate like such small region is very challenging. So how to solve the problem. So one way to solve this problem is to try to find the clue from the history. So here is like a very simple overview of the evolution of transformer-based segmentation models. So initially, like two transformer-based segmentation model, there was like a mask former and the mask two former, which added the mask attention in the transformer decoder. And these two models into like a parallel lines, they evolved into promptable segmentation model of SAM. Well, there was like a lot of like adaptation, but the mask decoder from SAM was mostly adopted from like a mask former in spirit. And the SEAM model, the segment everything everywhere model, which BiomedParse was based on, was adopted from the master two format, but also added a lot of other things to make it able to do like a promptable segmentation. But the clues can be found in this like line of history. So in max two former, and also the following work, the prompts are encoded in some of these like query vectors. And in the end, they are also used to decode the segmentation mask. So one key feature of the mask two former is that in the transformer prediction architecture, it used the mask attention rather than the full attention on the image. And this mask was from the foreground prediction. So let's say in every layer, the model have a rough prediction for the foreground, and the model will exclusively focus on this region for the cross attention, but ignore all other regions. And this static attention masking was originally proposed to help the transformer to localize. But from the experimental results of mask2 former, it seems that it struggles with small objects. So this is a performance chart, is a table from the mask2 former paper. And they divided the AP into like a small objects, medium-sized objects, and large objects. So while the model was good at medium object and large objects, in small objects, it's always like falling behind the best competing models. So we try to seek clue from like what happens with like this masked attention is that when the model is predicting a wrong foreground region, especially when the object is small, it's very, very easy for the model to miss the target. Then in that case, it's very hard for the model to recover because you are predicting a wrong region and you are exclusively attending to that region. Then it's hard for the model to pick up those like informations again in the following parts of the network. So because of that, we propose the Boltzmann attention sampling. So the key idea is still the same. We want to focus on a smaller region of the image to help the model to narrow down the search. So we sample first. We sample less than 10% of the total image, and then only attend to those sampled ones. So here is like a overview of the chart. So this is one layer of the transformer mask decoder. So the model will first estimate a Boltzmann distribution on the image. So this is like the shape of the image. So this is a spatial probability distribution in 2D, and randomly sample some patches, let's say 10% or less than 10% of the patches from this distribution. And the rest is exactly the same as a normal cross attention. Some latent query vector will cross attend to these like sample patches and update themselves and go to the next layer. The next layer will be another set of like updated query vectors. They do another refined guess and then attend to those patches. This gas refining allows like exploration and exploitation. In different parts of the model, we can use like a temperature parameter to control how much this distribution is like distributed across like the image. And this distribution is also a learnable probability distribution that we can train. So in some sense, it's like a two parallel attention mechanism. One is like a stochastic one by random sampling. The other one is the normal one, simply only by computing the attention scores. And here are some like concrete examples of the sampling. So we input a image to the model and prompt the model in like different text. And the model have a total, in this case, our case, a total 9 layers. So in some early layers, all the like these visible patches are the patches sampled by the model in that specific layer. So all the dark regions, the unsampled regions, are completely like a blank, completely discarded, and the model was never able to see that part of the image. And in the early layers, the model is trying to explore broadly on the image, and towards the middle layers, it becomes to concentrate a bit more on this like foreground regions, but still exploring like a lot of like other places. And towards the end, the last layer, the model is very, very concentrated in this foreground region, but also explore a little bit in other parts of the image. In the second case, we're trying to segment like pancreas in abdomen MRI, and it is here. So we can see that in the early layers, the model doesn't even hit like even one patch in this specific layer, but explore some like other regions. So it doesn't know like what a pancreas looks like in some sense. But in the middle layer, one of the sampling hits this target, and it's very quickly that a model can pick up the relevant information and know, okay, this is the relevant information I should go to, because the distribution is learnable. In the later layers, the model is quickly able to concentrate all this sampling into these foreground regions to get more information. So putting this like a attention sampling mechanism in the whole like model architecture gives us the so-called like Boltzmann model. So we input the image to get some like multi-scale visual features, and these visual features will be fed to this like a transformer decoder to generate the segmentation mask. So we initialize some different like queries in parallel. So these are all learnable embeddings from the model. And the other parts are the text embeddings from any like language encoder. So you can encode your prompts in a few like text embeddings. And then they just all go through like self-attention layers to exchange information. And in every layer of the model, like these latent query vectors will estimate a probability distribution as described in the previous slide, and randomly sample some like patches from the image, and only use those sampled patches as the key and value for the attention calculation. And then they are updated and go to the next layer. So throughout the layers, we control a sampling temperature like T. In the early of the layers, this temperature is very high. So that means this distribution is almost like uniformly distributed on the image. So the model can, because in the early layers, the estimation, the probability estimation of the model is very, very crappy. So you never know like where you should focus on. So in that case, you just explore. You just sample like different parts of the image to gain information. And towards the later part of the model, we lower the temperature such that now the model have a better estimation of the probability distribution. We should just exploit those part of the image. So that's like shown in like these like layer 8 sampling cases. And in the end, the model it can help the model to learn how to focus on like those small areas. And here are some like performance improvements outlined. So we compared like this Boltzmann sampling to like a traditional like a full attention. So simply pass all the image batches to the cross attention model. And we also compared with a static thresholding from like that was used in previous work. And we also compared the improvement of the model in specifically in locating small objects. The definition of small object is less than 1% of the image area. And we see that, these are all like a text promptable segmentation. We used the exact same text module and image encoder for all these baselines, but only used the mask decoder part of SAM2 and SEAM and compared with like our proposed methods. And we can see that on large objects, the SEAM and the Boltzmann are almost the same, but on small object, the advantage is like more obvious. Here's just one example of the small objects, which like a BiomedParse was missing, but with the Boltzmann architecture, we're able to like precisely locate small objects in the image without any like a spatial guidance. So a quick summary here. So Boltzmann can segment small objects with only text prompts and is very efficient in localization with the Boltzmann attention sampling mechanism. And it can outperform like segmentation mask decoders in SAM, SAM2, and SEAM. Yeah, I will take a pause here. But it seems like there's only 10 minutes. I have like some like more contents to cover. Maybe I can
Yeah,
leave.
I think Theodore, maybe you just go ahead and finish it.
Yeah.
Yeah, finish your presentation, and then I think we still have like, yeah, 17 minutes total, right, for the presentation and answering questions.
Okay.
Yeah,
Yeah.
maybe you can go ahead and finish.
Okay. Thank you. So in the third part, I will introduce how to go from like a 2D model to 3D segmentation. So this is the work in a like a CVPR 2025 challenge of text-guided 3D segmentation that we participated in. Oh, sorry. So what's the challenge in the 3D segmentation? So the challenge can be different for different models. So if you use a 2D model, try to do 3D segmentation, the challenge is that because 2D models by default assume the existence of the object in the image, so the false positives can accumulate slice by slice. So in a 3D volume where there are a lot of slices where the object doesn't exist in the image, you can see like a big part of like false positive segmented regions. And another like a very obvious challenge is that a 2D model lacks the information from the 3D context. You don't see the neighboring slice, you don't see the full shape of the object in like a larger like a 3D volume. So those information like limit is true for the model and very critical. And for the 3D model, it's totally another different story. So you will face the challenge of like high memory consumption. What comes with that is that you have to train with much smaller batch size, and sometimes that can be challenging for training, let's say, especially like transformer-based models. And in order to address that, sometimes you need to sacrifice the resolution, but that will also downgrade the performance of the segmentation. And with 3D with 3D data, you have smaller effective data size. So let's say you have like 10,000 volumes. Each volume contains like, let's say, about 100 slices. So if you split them into like 2D slices, you have effectively 100 times the data size to train your model, and that can also make the model training more efficient. And also 3D model lack a very good pre-trained foundation models from general domain, because like most of the general domain models are in 2D. So this is also a big challenge. So our solution is try to avoid some of the challenges in each of the world, and we also want to leverage the success of the existing 2D framework that I introduced in the previous part of the presentation. So the solution is that to rethink like what's the interaction between model and data. So in every the canonical machine learning framework is that you have a input, you want the output. So so traditionally you will think like the input is the data goes to the model is a function gives you output. But actually it's combined of the two. It's your model plus your data jointly give the output. This can be a bit abstract, but we can think of like in this format. Let's say Y is your output, F is your model, and Fx is how the model take the data to the output. But that's not the full story. So let's say if X is the data represented and fed to the model, you can optionally represent your data in different ways. That becomes so let's say X equals to phi big X is the representation of the original data that's fed to the model, and this big X is the true information existing in the data. So yeah, one quick example is the dimension of the boundary box example. So let's say the location, the coordinates of the boundary box is this big X. So that's the real information in the origin in the input. And the positional embedding that's trying to embed the coordinates of the boundary box is this phi. That's representing this original data in a different form. So, and in that case, that this X becomes the positional embedding, and then that's fed to model for a good purpose. But I'm just taking that as an example, but that's not what we are doing here. But in the same idea that the actual representation from the data to the output is actually a joint function of the model function and also the data representation of the original information. So by decoupling these two parts, what we want to achieve is that we want to use similar or like mostly similar model architecture. So we want to keep F the same, but we want to use different format of the data. So we want to find a good phi function to represent the data, to represent the 3D data, and make that more efficient for our model to solve the previous, let's say, lack of like 3D context challenge. So the way we do this is the model is still 2D. We process one image in 2D, text prompt, and output segmentation mask also in 2D. But in each image, we try to compress the information from the neighboring slices, or like one half each is like one half of the 3D context into like one single image. So let's say I want to perform a segmentation on this slice. We call this one the focal slice. Is the one I want to focus on. All the neighboring slices, so all the slices above and all the slices below, they are downsampled in a specific way, and then all compressed into this image. And that way, we can utilize exactly the same 2D model architecture, but achieve some like and try to insert some information in 3D volume. And this is the so-called like fractal volumetric encoding. So we have a one focal slice, and we have like some neighboring slices like 1, 2, 3, 4, 6, 4, 5, 6, and so on and so forth in two half of the 3D context. And we adaptively downsample them in groups. So these three, they downsample like by one half, these three they downsample by 1/4, and so on and so forth. We can do this we can do this for forever, but to the limit of like the resolution, the physical the limit of the resolution. And after they are downsampled, we pack them like recursively. So let's say we pack everything here to here and then combine them into a bigger image, pack everything here, combine them into a bigger image. So one half of the 3D context is ultimately going into like one channel in a RGB image, and the same for the other half. And the focal size will retain the original resolution and go to the third channel of the image. So that way we can compress a 3D volume centered around the focal size into a 2D RGB image with exactly the same with the same size, the same shape of the image, but with some like a 3D context that's included in. So this way, it's actually, we want to build a mathematical equivalence to doing a 3D convolution. So in this example, so each of them, let's say, is one part of one slice. So this is slice one, slice 2, slice 3, so on and so forth. Because these like top ones, they are downsampled, so they contain like a less pixel or voxel number of voxels. And by arranging them in the specific way described in the previous slides, they could become a patch in 2D. So in many of the modern vision model architecture, the first layer of the model is always doing disjoint patching. So for example, in like a VIT, VIT split the image into patches of like a 16 by 16 or 14 by 14, or sometimes smaller, but it's always a fixed number of patches that's dividing the image. So two patches never talk to each other. And the first layer after the patching is always to flatten the patch, the pixels in the patch, and then do a linear transformation into the so-called patch embedding. So after flattening this, like the pixels in the patch, they become no different than doing a 3D convolution, but with some downsampling. But effectively, it's doing the same thing. It's a weighted sum or weighted average, or it's a linear transformation of all the pixels or voxels in this in the original space. But with some like adaptive resolution downsampling. So because of that, in packing the image in this way, we don't lose the capability of the model to get the 3D neighboring context, but we can utilize the exact same like 2D model architecture. So here is an example of the encoding and decoding of the image. So the encoded image is a RGB image in this way. If you like zoom in, you will see some neighboring sites. There are some patterns here, and this image can decode exactly to this full set of image. There is a focal slice of the full resolution, which is the one we are going to perform segmentation on, and there are slices with like half the resolution downsampled by half, and resolution downsampled by like 1/4, and also the slices on the other side, other half of the 3D context. So they contain the exact same amount of information without any loss. But these ones, they are downsampled. It's hard to see it on this slice. Yeah, but this is one example. And after that, we feed this like encoded RGB image to the model, and to perform segmentation and slice filtering. So we used the previous dimension, the Boltzmann to perform the segmentation. But another challenge in 3D is that a lot of the slices are empty. So let's say I prompt the model esophagus in CT. It could be it doesn't exist in this slice, and the majority of the slices are actually empty. So we need a classification head to determine the existence of the object. So in order to train this model, there are two training objectives. One is on the positive slices, we have the segmentation loss and also the classification loss. On the negative slice, we don't have segmentation mask, so there's only the classification loss with label 0. And on positive slice, this classification loss is also always with label 1. So the problem of this is that if you train with a lot of negative slices, it could harm the segmentation performance because there is no loss supervising the segmentation module. So the key here is that we have the gradient cutoff. So when doing the classification training, the loss doesn't back propagate to the segmentation module. So we maintain the same quality for the segmentation, but also have the model to decide where if the object do exist in the specific slice. So we train this model on this like CVPR 2025 text-guided 3D segmentation challenge datasets. This is the datasets containing like 5 different modalities like CT, MRI, microscopy in 3D, PET scans, and ultrasound in 3D. They were collected from many different open source datasets. And the total number of like volumes and also the number of slices that we created in the aforementioned way is like a few millions. So this is pretty big data sets to train the model. And after training the model on these data sets, we have some like a semantic segmentation comparison with other like a text prompted 3D segmentation models. And our model was able to outperform the baseline models. And this is the evaluation in NSE, the previous ones in the DICE score. And there was also the instant segmentation evaluation evaluating by the F1 score. And our model was able to outperform in most of the cases, especially in CT and MRI. But in PET scan, it's falling behind the SAT model trained with all the data. And this one is the DICE score on the true positives. And our model was able to outperform in most of the cases, but in the PET scan. And we submitted our model to this like CVPR challenge, and we also got some like testing results on the hidden test data sets. And the overall performance of the BiomedParse model was also good compared to other baseline models. But on the instant segmentation F1 score and DICE score, it's still like challenging for all the models. So some like a quick examples showing what the model is doing. So the model is prompted in different with different text prompts and is able to associate each region with a specific text prompt in this way. And this is a abdomen CT scan example, and this is like a lesion in PET scan, and this is like a lesion in CT scan. Some failure cases. In this case, like two nucleus are touched together because the model only does binary semantic segmentation. It doesn't do any instance segmentation. So it doesn't know how to split the instance into two. And sometimes this like touching instance can cause the problem because of like this like over segmentation. Another failure case is that this is a MRI showing like the right humeral structure because we train with like augmentation, like with flipping, rotation, and also the 3D context encoded by this like volume fractal encoding. It contains some 3D context, but not the real 3D context. So sometimes like this, the symmetry can cause some problem for like a left and right. And just a summary. Uh, and we, in this presentation, I introduced the work that try to unify biomedical segmentation tasks with language. And the first one was BiomedParse, which proved it's possible to unify different segmentation tasks and modalities with only language. And also, I introduced the Boltzmann, which is a transformer mask decoder that can locate small object without spatial prompting. And in the last part, how to use 2D model with 3D context encoding and achieve like a SOTA result in the text prompted 3D segmentation. I will also mention there are still some remaining challenges, for example, generalization to unseen tasks and better instance segmentation, the incorporation of the real 3D context information.
All
Yeah,
right.
that's
Mm. All right, yeah. Thank you, Theodore, for the great presentation. I think this meeting is a little bit longer. Let's stay a little bit longer to finish all the questions. So, Theodore, can you stay longer? Let's finish some of the questions, then we conclude this session. So, I'll read the questions. So, one question is, can BiomedParse segment object that hasn't been trained on before?
Yeah, very good question. As I mentioned in this remaining challenge part, so this is still a it's still a existing challenge, because what we observe is that if you train model with some specific task or similar task, it's able to performance this type of segmentation. But if you don't train with specific task, because of the variety of the biomedical concepts or terminologies sometimes can be very, very different. So it's a bit challenging for the model to adapt to a completely unseen task. But similar tasks, sometimes, okay, for example, describing like different parts of the organ, like the whole organ or the parts of the organ, sometimes it can build a relation, but in a completely new terminology, is not very good in generalization to those tasks.
Okay. And a similar question is, what happens when you ask a biomedical to segment the pathology that are not present in the image? Does it recognize that?
Yeah. In the original version, what we did was the training data always assume the the prompts corresponds to one part of the image, and we have a post processing step that's comparing the statistics on the segmented region. For example, like what's the probability output from a model and what are the pixel levels in that region, and compared to a predefined like a ground truth. For example, I know what's the statistics from the training data sets, like the segmented tumor region, and that we can compare with the output from the model to determine if that's a false positive or a true positive. But it was not natively built in to do the classification. But in the 3D segmentation, if you think about it from slice by slice level or volume by volume level, it's able to determine if the prompted lesion is not exist in the image.
Okay. And another question is, in your motivation, you mentioned that the advantage of the Boltzmann approach is that the denominator in the softmax function doesn't become too large because it's normalized only over a small number of samples, right?
Yes.
But maybe you'll face issue when computing the Boltzmann distribution since it also involves a large denominator. That
Uh,
problem?
Yeah. So in order to compute the Boltzmann distribution, it is actually less sensitive to that because I can allow I can allow a very rough estimation of the distribution because I can control the temperature. I can encourage the model to explore even some area with relatively lower probability by tuning the temperature up in the early of the layers. Um, so that way the model can hit those regions. And in later part of the layer of the model, the temperature is cooled down so that they focus on good parts of the region. And another key design to make this work is we initialize the multiple different queries. So it's not just a one distribution estimation. So let's say I initialize like 10 queries. Each of them will independently estimate a Boltzmann distribution and draw the patches independently. So each one of them will attend to possibly different parts of the image. And after each layer, they are go through a self-attention layer to communicate the information. So that's to say, if let's say one of them hits on the relative parts of the image that already got some relevant information, those information can quickly propagate through all the like different queries. So that's why after it picking up the relevant information, it will quickly learn to focus on that specific region in the later parts of the model. And the segmentation mask independently will be independently predicted by all these like different query vectors, and they are like aggregated together, either with like simply averaging or some like a few like convolutional layers. Yeah, that's another design.
Okay. Okay. Yeah. Thank you, Theodore. And then let's move to your third part of the presentation, some questions. So does the fractal encoding include the entire volume or just a small number, a small subset of the contiguous volume around the focal volume? And a
Yeah.
similar question is the fractal encoding only done in one dimension, or do the other dimensions show the artifacts or other undesired effects?
Okay, let's address the first question. So it depends on how far you go. So you can always stop at a certain slice. Because if you go like go forever, theoretically you can go through all the slices, but the faraway slices they will be downsampled to only a few pixels, or like to the level that's is not very meaningful it's not already it doesn't contain any meaningful information. So you don't want to go too far. So in our experiment, we just uh, experimented going like one layer or two layers or three layers. So yeah, like at most in three layers. So if you go smaller, then that's contains like the fewer slices. The extreme case is that if you just go one step, is just the neighboring slice in RGB, so like three slices. So if you go one more step, you have like six more slices. So like let's say you encode like twice, you get six plus, it's like nine slices. If you go further, it's like 15 slices. So it depends, but it's a trade-off. You go further, you have more slices, but those are in lower resolution, so you want to stop at some point.
Okay.
Uh, the second question,
Yeah, is the fractal encoding done in one dimension?
yeah. So the dimension is you can optionally determine how you want to encode. So let's say in CT, usually we just go the axial view. So we go through like the Z dimension. In other, let's say MRI, you can pick the dimension that you want to slice through. So basically, it's the best slicing, or you can. So in our model training with this data, we automatically determine what's the best axis to do the slicing. And sometimes we do multiple slicing. For example, we slice one 3D volume in like a two or three different axes and provide those to the model. So the model learn like different views and how to perform segmentation in different views. But in the inference time, we will always pick one axis, one dimension, and then segment through that dimension and simply stack them together.
Okay.
Uh, I hope that answered the question.
All right. Yeah, because of the time limit, let's answer the final question. So biomedical data sets are often limited, so we rely on data from multiple institutions. However, this data set may differ from each other. For example, data set A, maybe
Mhm.
MRI prostate cancer that include virus text reports, while the data set B may only contain images. how can
Mhm.
handle missing or inconsistent text annotation when
Mhm.
training or fine-tuning a segmentation model,
Mhm.
and how we can verify or unify or even validate the quality of text prompts in such
Mhm.
cases. Yeah,
Mhm.
good
Yeah.
question.
Yeah. So I want to mention that the text prompts are not from any text in the data sets. So it's all them are like pre-structured with what's the segmentation task and what's the modality of the image. And those prompts are created by the LM, so not from the original data sets. So it is okay that let's say the original data set doesn't contain any text information, that's okay. As long as there are like some class definition, we can always use those information, the structural information to generate the text prompts. So that way we also maintain the quality of the text prompt in that way. So it's not the raw text, but I know it is it is a very good idea that we use some existing image and text pairs that's existing, and to in the case where segmentation annotation is lacking, we can use this as like a multimodal alignment training to achieve similar goals. So in that case, like the quality of the text is very important, but it's not that important for our specific work.
Okay, yeah, thank you, Theodore, for the explanation. So yeah, so again, thank you, Theodore, for the great presentation. Yeah, let's conclude this today's MICCAI industrial talk, and we thank all the audience for attending, for asking questions. Yeah, and yeah, let's stop here. Right. Thank you.